For nearly a century, the name Albert Einstein has been synonymous with genius. Even children know it. But few understand the meaning of Einstein's theories, or why his name has taken on an almost mythical significance in our culture.
What is light made out of? Why doesn't the moon fall down? Why do I have to grow older? Why can't I just grow younger? Is there anything else besides the universe?
When my daughter was 2, I used to try to answer these questions. But now that she's 5, I answer, "Would you like some ice cream?"
They're always asking why. Why? It's cute at first, but then they can get irritating.
Sometimes their questions make me feel a little stupid. I guess it's because I don't know the answers.
We call ourselves grown-ups, but sometimes, as our bodies grow, our minds shrink from the big questions. A few philosophers and scientists have not only continued to ask the questions, they have actively sought the answers. Science is, after all, an attempt to describe the universe. At the beginning of the 20th century, a young patent clerk in Bern, Switzerland began to ask and answer some very big questions. And in doing so, changed the way we perceive the world. He also changed the world itself. His name was Albert Einstein. It's hard to believe, but true, that when he and other young men began their careers in the field of physics at the turn of the century, they were told that it was a limited field because all the great discoveries had already been made. Part 1. Einstein's special theory of relativity.
We're told that Newton learned a lot about the physical world when an apple fell on his head. That probably didn't happen, but the apple is a good symbol of classical physics. It's solid, and we can see it. And the perceptions of the physical universe at the end of the 19th century were the classical ones, the ones that had been formed 2 centuries earlier by Newton and Galileo. Their theories described, among other things, the way objects move in time and the measurements of such motions. They took into account, these theories took into account that such measurements are going to differ from one set of observers to the next. And these measurements that differ are called relative. Other measurements are going to be the same for all observers, and these measurements that are universally agreed upon, they called absolute. Take the motion of an object, for example. Whether or not an object is moving depends on the observer. According to Newton's physics, there's no meaningful way to say whether an object is really in motion or is at rest. Despite this, Newton seemed to have a need to believe that there was a meaning to absolute rest. Einstein showed that Newton's ideas about space and time ultimately were wrong. But to understand what it was that Einstein did, we have to understand what Newton's ideas of space and time were. To do that, we're going to get some help with this example of a moving train. Hi, Haley.
Hi.
Want to play a little game of ping pong and help me illustrate something about physics?
Okay, but I don't have a paddle.
Well, I only want the ball to be moving in one direction. So this is going to be a special game of ping pong. It's going to be one-sided.
Well, it won't be ping pong. It'll just be ping.
Okay, then let's play a game of ping. Okay?
Okay.
Okay, when I hit the ball, it travels about 1 meter between bounces, and it takes about 1 second. So we here on the train see the ball moving at 1 meter per second. But outside the train, things are different. Let's go outside the train. The train is moving at 40 meters per second. We'll soon pass 2 farmers, 41 meters from each other. Now, for the purposes of this demonstration, we're going to slow
time down to 1/10 its normal rate.
To a system of observers on the ground, the ball travels 41 meters between bounces. The distance between these 2 events is relative. It's different for me and for them. But the time between the 2 events remains 1 second for all of us. It's absolute. In this relativity, the relativity of Galileo and Newton, it follows that the speed of the ball is relative. Different distances, same time. This is the so-called classical viewpoint on space and time, the relativity of Galileo and Newton. The 17th century theory was still taken to be the last word in relativity at the beginning of the 20th century. And there were 2 reasons for its longevity. First, it worked pretty well. It gave predictions that were in agreement with the most precise measurements that could be made. Second, it just had to work. It was, after all, obvious that speeds were related the way they were in our example of ping pong balls moving in trains. But a problem. an embarrassment arose at the end of the 19th century. It was a problem of electromagnetic waves, waves which, depending on the wavelength, we call radio waves or infrared radiation or ultraviolet rays, or most often light. It was well known that light was a wave. It had all the behaviors associated with a wave. Of course, waves must be waves in something. At the seashore, we see waves that are motions in water. When we hear the cry of seagulls, we're receiving sound waves that are motions in air. Physicists invented something which had, as its only job, to be the thing that light was a wave in. They gave it the big fancy name, the luminiferous ether. It was something that had never been observed before, and as it turned out, something that never would be observed. It was supposed to be for light, what water is for ocean waves, what air is for sound waves. If the Earth was moving through this ether, light should travel at different speeds when aimed in different directions. The American physicists Michelson and Morley, early in this century, carefully measured the speed of light sent in all directions, and they found it was always the same. Could this mean that the Earth happened to be sitting still in the ether? This was ruled out by other experiments, and the world of science was left in chaos. For us here on the train, the pulse of light travels about 1 meter. For the observers outside, the light, of course, travels further between the time it emerges from the gun and the time it hits the paddle. It's the same as we saw with the ping pong ball. But if those on the outside see the light go further in the same time, then they are observing light to move more quickly than we do here on the train. This directly contradicted the findings of Michelson and Morley. It was a time of desperation, and the explanations scientists came up with were as unsatisfying as they were contrived.
Classical physics had shown that objects, like ping pong balls, should move at different speeds relative to different observers. But Michelson and Morley had recently demonstrated that light does not behave this way. Its speed is always constant, relative to every observer, no matter how fast or in what direction the observer is traveling. The world waited for someone who would see through the fiction of the ether to a new view of the universe. Albert Einstein was born in Germany in 1879, the son of a minor industrialist. At school, young Albert hated the rigid demands for mechanical repetition and cramming for exams. As a result, some of his teachers thought he was stupid. The popular legend that Einstein was a poor student has given comfort to parents all over the world. But in fact, it's not true. What is true is that Einstein was highly self-motivated and utterly fascinated from a very young age with theoretical subjects. By the age of 10, he announced his intention to discover the laws of nature, and by 15, he wrote a paper trying to reconcile the major streams of 19th century physics. However, it is also true that in the harshly discipline-based educational system of pre-war Germany, the young Einstein was something of an anomaly. His resentment of that entire militaristic society was no weaker than the resentment which some of his teachers felt toward him. When Einstein's family moved from Germany, Einstein was admitted to Zurich's Polytechnical Institute on the strength of his math scores alone, despite the fact that he held no high school diploma. Following his graduation from the Polytechnic, Einstein was the only member of his class who was unable to secure a teaching position anywhere. He was forced to take a rather tedious job at the patent office in Bern. He also married a former classmate from the Polytechnic named Mileva Marek. But their marriage soon revealed itself to be an unhappy one, and it was to end in 1914. While he was employed at the patent office in Bern, he formed deep friendships which would last the rest of his life. And in his spare moments, he ruminated about the enigmas of classical physics.
Remember the train and those farmers? Well, it isn't really all that difficult to understand how Einstein explained the paradox of light speed. He pointed out that the observers on the outside of the train do indeed see the light pulse travel a greater distance, but they also see it take a greater time. To the farmers, the event must take longer than it did for Haley and me, because the speed of light, as Michelson and Morley had found, must remain constant. We can't have it both ways. If we want the speed of light to be absolute, to be the same for all observers, then time cannot be the same for all observers. Alone among the physicists of his day, Einstein resolved the paradox of light speed not by changing a detail of electromagnetism, the theory describing light, but by changing our view of the nature of space and time, and the consequences were very disquieting.
One of the revolutionary ideas Einstein came up with in 1905 was this resolution of Michelson and Morley's findings with classical physics. Time, he said, must move at different speeds if light always moves at the same speed. This affects not only laser guns, but also everyday occurrences. The simple act of traveling on a train, for example, makes time move at a different rate for you than for people in the towns you travel through.
Suppose, for example, both ping pong players smack the table with their paddles at precisely the same time in the train system. Ready, Haley? 1, 2, 3. In the train system, the elapsed time is 0. The events are simultaneous, but not to the farmers. The farmer on the right measures the slam on his side of the table to happen slightly later. The delay is only about a half of a millionth of a billionth of a second. So it's not very important for daily schedules, but it is enormously important to a view of the way things are. It says that simultaneity is not an absolute concept. These claims about time and space are no longer controversial. They're demonstrated with high precision every day by particle accelerators, by cosmic ray detectors, and by the other instruments of today's physics. Scientists can study, for example, a subatomic particle with a half-life of a billionth of a second. That is, a particle that lives a billionth of a second when it's at rest in a laboratory. If that particle, say in the form of a very high-energy cosmic ray, shoots through the laboratory at a very high speed, it can be measured to have a lifetime as long as a full second. The mathematics of the new relativity, Einstein's relativity, was simple. It was mostly at the level of high school algebra. But to suggest this vision of the physical world required genius and audacity. It amounted to claiming that what our intuition demanded to be true of space and time was not, in fact, the way the physical world worked. Scientists would never again trust common sense as a reliable guide to what could and could not be.
Common sense says that time is the same for everyone, everywhere. Einstein proved it is not. In the 1970s, 2 atomic clocks, incredibly precise in their time, were used to test Einstein's theory that time slows down with increased velocity. When the clock on an airplane having traveled around the world was compared with a matching clock at the starting point, the traveling clock showed an earlier time than the stationary one. When Einstein published his insights into space and time, his so-called special theory of relativity, he was unknown in the academic world. Soon his career flourished. He met the leading physicists of the day. Albert Einstein was not your usual scientist. Instead of performing experiments and evolving theories to explain the experiments, Einstein examined the world through his thoughts alone, much in the manner of Plato or Socrates. While Einstein was developing the special theory of relativity, another great thinker, Henri Poincaré, was thinking in a very different way along very similar lines.
Einstein's theory of relativity was the first new scientific idea quickly circulated in the 20th century world of expanded communications. The press exploited the most sensational part of Einstein's theory, that time did not exist. For instance, an English newspaper joked that watches and clocks should be discarded. Here in France, a cartoon showed an old lady who said that thanks to Einstein, she had no more worries about wrinkles. Beyond the jokes and the uproar, scientists quietly explored the implications of Einstein's theory and extended them in new directions. One of the new directions came from the work of a Frenchman, Henri Poincaré, like the Dutchman Hendrik Lorentz, had been thinking along similar lines about relativity even before Einstein published his special theory of relativity. Here we can see the date, 1905. Here we can see the mathematical formulas that introduced the concept of four-dimensional space-time. Poincaré's work was later developed by the German mathematician Hermann Minkowski. One way it extended Einstein's thought was to show that beyond the celebrated relative or observer-dependent features of the theory, there was a deeper, absolute, observer-independent structure. According to Einstein's theory, the time of a moving observer appears to slow down relative to an observer at rest, and objects seem to shrink in the direction of their motion. These are all observer-dependent consequences of Einstein's theory, but Poincaré and Minkowski found structures which would be the same for every observer. These observer-independent results came to be embodied in what is now called the Minkowskian geometry of space-time, without a hyphen, indicating that space and time are not separate entities but simply complementary aspects of the same thing. In the space-time view, the basic concept is that of an event, that is, something that happens at a certain time and at a certain place. Take, for example, the train in which Richard Price and Haley were traveling when we last saw them. Suppose another train is coming in the opposite direction. According to Einstein's special theory of relativity, the prediction of where or when these trains will cross depends on the position and velocity of the observer. They will cross in different places for observers moving at different speeds. However, one absolute statement can be made. Assuming the trains do not stop or turn, they will eventually cross, and their crossing defines an event. Space-time is defined as the collection of all possible events. Space-time has four dimensions. The three spatial dimensions of height, width, depth, time being the fourth dimension. Without the work which Poincaré began as early as 1905 and which Minkowski expanded upon in 1908, Einstein would never have been able to develop the ideas put forth in his special theory into the more global general theory of relativity.
In 1913, Einstein was offered election to the Prussian Royal Academy of Sciences and a professorship in Berlin, despite opposition from the anti-Semitic and conservative members of the German scientific community. 5 months after Einstein accepted the academic post and moved from Switzerland to Germany, war broke out. In Germany's patriotic and belligerent climate, the pacifist Einstein campaigned against the fighting. Einstein was often naive about human affairs. After the armistice in 1918 ended World War I, Einstein was convinced that militarism was a dead issue for Germany. His unceasing advocacy of pacifism made many enemies in the German scientific community. Later, Nazis would try to make him a laughingstock, calling the theory of relativity wild Jewish imaginings. He was castigated for his Bolshevism in physics. In 1920, Einstein heard that his cousin, an 8-year-old girl, was disappointed not to have met him. He sent her a postcard with a description of himself.
Pale face, long hair, and a tiny beginning of a paunch, in addition to an awkward gait. I usually have a cigar in my mouth. But crooked legs and warts I don't have. Also no hair on my hands. So I'm quite handsome.
At about the same time, Einstein described an important thought which led to another of his great theories. Part 2. Einstein's general theory of relativity.
In 1907, I was sitting in a chair in the patent office in Bern, and all of a sudden there occurred to me the happiest thought of my life. If a person falls freely, he will not feel his own weight. I was startled. This simple thought made a deep impression on me. It impelled me toward a theory of gravitation.
To understand Einstein's happiest thought, imagine our friend Haley standing on a meadow near the edge of the cliff. In the meadow is a toy cannon, blasting the cannonball 5 meters into the air. The trajectory is called a parabola. Now, a part of Einstein's happiest thought was his discovery that this trajectory is not really a parabola, it's a straight line. A straight line? That's crazy, you might say. But Einstein's apparent craziness was really a deep insight into nature. Einstein realized that the laws of physics will always look simpler to somebody who is falling than to somebody who stands with feet firmly planted on the ground. In some sense, the laws of physics prefer the viewpoint of a falling observer. They prefer Einstein's viewpoint. Or, to put it another way, nature liked Einstein's way of looking at the universe and not yours or mine. Now, if we can think about physics from a falling viewpoint, we will be led quickly to a much deeper understanding of nature. Imagine Haley back in the meadow. She picks up a window and holds it in front of herself. Are you ready, Haley?
I'm ready.
She then steps forward off the cliff just as the cannon is fired. And as she begins to fall, she watches the ball through the window. Now let's slow things down and look closely at what Haley sees through her window as she falls. The ball's trajectory is indeed a straight line relative to the window and not a parabola. It's a straight line as seen by Haley, the falling observer. Now, to you or me, this insight is just cute. But to Einstein, it was powerful. To understand its power, let's consider the properties of straight lines as described by Euclid's laws of geometry. If we have two straight lines and they initially are parallel, then they never will cross. They'll always remain parallel. Or at least this is so if the lines are drawn on a flat plane as they are here. On the other hand, if they're drawn on a hemisphere or on any other curved surface, then they will cross. It's the surface's curvature that is forcing them to cross. Now, is the three-dimensional space in which we live curved or is it flat? This was the question to which Einstein was led by his happiest thought. To answer the question, we can follow the straight trajectories of two cannonballs and see whether they cross. Imagine Haley back in the meadow with two cannons. She grows larger and larger until she's a tenth the size of the Earth. The cannons then fire their two balls into the air along precisely parallel trajectories. And we have arranged for two Earth-eating moles to tunnel their way down through the Earth ahead of the balls. Although the balls initially were moving parallel to each other, they're both pulled by the Earth's gravity toward the Earth's center. And there they collide. Now, it is gravity that makes them collide, according to Newton, but Einstein takes a different view. Einstein regards the ball's trajectories as straight lines that initially were absolutely parallel, but they are being forced to cross by a curvature of the three-dimensional space in which we live. We can visualize the curvature at work by imagining our space and the Earth and Haley as two-dimensional, not three. The Earth and its space are actually bent in a higher dimensional hyperspace that we and Haley living on the Earth have absolutely no ability to perceive. The cannons fire their balls. The balls move along straight lines. The lines initially are parallel, but our space's curvature makes them cross. Now, both viewpoints are correct, Newton's and Einstein's. What Newton called gravity, Einstein called the curvature of space. Gravity, in fact, is caused by the curvature of space, Einstein tells us. But actually, I'm cheating a bit when I say this. Really, Einstein regarded space and time as combined into a unified space-time that is absolute. And it is the curvature of this unified space-time that causes gravity. Einstein developed a detailed mathematical theory of gravity based on space-time curvature, a theory that has come to be called the general theory of relativity. When the curvature is gentle, it produces the kind of gravity that we're accustomed to, the gravity that holds us to the surface of the Earth. But when it's strong, the curvature produces new, unexpected things of which Newton never dreamed. The curvature produced by all the stars and all the other matter in our universe may close the universe up upon itself, like the surface of a balloon. Einstein's general relativity predicts that the universe was created as a tiny point. and exploded outward, growing larger and larger until it became as we see it today. When a massive star exhausts the fuel that keeps it hot, it implodes to form a black hole, a hole in the curvature of space down which things can fall, but out of which nothing can ever come. Now, general relativity tells us a lot about black holes, but it has not yet told us what the bottom of a black hole should look like. Two black holes orbiting around each other should create ripples of curvature that travel outward into the universe, carrying a symphonic image of the holes and of their motion. These ripples are called gravitational waves. "75 years after Einstein predicted gravitational waves, physicists have taken up the challenge of detecting them and decoding their symphonies. The universe closed on itself, the Big Bang, black holes, gravitational waves. Einstein never dreamed of these concepts in 1915 when he gave the world his general theory of relativity. Nevertheless, they are inevitable, marvelous consequences of his theory."
In the midst of World War I, when he published his general theory of relativity, Einstein offered a crucial prediction by which it could be tested. He predicted that when a light ray from a distant star passes near the sun, its straight-line trajectory should be bent by the curvature of space. In 1919, with the war over, a team of British astronomers photographed the sky near the sun during a total solar eclipse. Their photographs verified Einstein's predictions. Starlight is, indeed, deflected by the sun's curved space. Soon after this triumph, Einstein began a series of trips abroad which brought him into contact with the famous and powerful. In 1922, he received the Nobel Prize in Physics. In the media, Einstein had become the first true scientific celebrity of the 20th century. As much as Einstein may have enjoyed the pursuit of the press, it once was too much for him, and he responded rather graphically to a photographer. Not at all embarrassed by its widespread publication, he used it for a Christmas card. Back home in Germany, Einstein did not find a climate conducive to either scientific study or the publication of his ideas. In fact, with financial chaos, the rise of Hitler, and rabid anti-Semitism, it was time to think about living elsewhere. Although Einstein was denigrated in Berlin, he was in great demand in other European cities. During his travels to Paris and London, his lectures were so popular that one impresario offered him a 3-week booking at the London Palladium. He is seen here with George Bernard Shaw.
Ptolemy made a universe which lasted 1,400 years. Newton also made a universe which has lasted 300 years. Einstein has made a universe, and I can't tell you how long that will last.
It is of great importance that the general public be given an opportunity to experience consciously and intelligently the results of scientific research. Restricting the body of knowledge to a small group deadens the philosophical spirit of a people and leads to spiritual poverty.
Einstein came to America in 1931 with his new wife, Elsa, who would remain by his side throughout her life. The purpose of the trip was to meet with Edwin Hubble, the famous American astronomer after whom the recent space telescope was named. Hubble had published proof that ours was not the only galaxy, and that the universe was expanding, as predicted by Einstein's general relativity theory. While at Mount Wilson, Einstein heard the Belgian scientist Lemaitre detail his theory that the universe had been created by the explosion of a primeval atom and was still expanding. Einstein jumped to his feet, applauding.
This is the most beautiful and satisfactory explanation of creation to which I have ever listened.
Einstein's public statements once again modestly ignored the scientific importance of the meeting.
Die Hochachtung für die bedeutenden Physiker und Astronomen dieses Landes, die in den letzten Jahren der Wissenschaft so bedeutende Fortschritte gebracht haben, habe ich von Europa mitgebracht. Die Freundlichkeit, die mir hier von allen Menschen zuteil wurde, kannte keine Grenzen. Herzlichen Dank und auf Wiedersehen.
Dr. Einstein and I, through Paramount News, take the opportunity to thank our many friends of the United States for the innumerable kindness they showered on us. We promise you, as best, if you want us to return, we shall do so soon.
During the 1933 trip to California, Einstein's affiliation with Germany was permanently severed. He learned that Jews were barred from civil service and that his country house had been confiscated.
I do not wish to live in a country where individuals have no legal rights, freedom of speech, or academic freedom. The situation in Germany today is one of mass mental illness.
Back in Berlin, a newspaper displayed this headline: "Good news from Einstein. He's not coming back." So Professor Albert Einstein settled at Princeton University's Institute for Advanced Study. The media continued to hound him. He set a lifestyle there that remained unchanged for 20 years. He lived in a simple two-story house, walked to his office, and for relaxation played the violin or went sailing. He rarely traveled, letting the world beat a path to his door in New Jersey. Meanwhile, the scientific world was moving fast in its appreciation of Einstein's genius. Studies in radioactivity and discovery of the existence of the neutron were supportive of Einstein's famous equation, E equals mc squared.
1 kilogram of coal, about 2 pounds, converted entirely to energy, was envisioned to yield 25 billion kilowatt hours of electricity. Uranium, which is a high atomic weight, is radioactive, which means that its mass tends spontaneously to convert to energy. But according to Einstein's theory, any mass can be converted to energy, even this turtle. Matter and energy are interchangeable. Indeed, they are two aspects of the same thing. If matter sheds its appearance of having substance, we call it energy. If energy congeals and takes on a different form, we call it matter. A small amount of mass, like our turtle friend, could theoretically be turned into a nuclear weapon if you convert it all to energy. But don't worry, Mr. T. You're not in a convenient form for conversion. No one's figured out how to do it. E equals mc squared made the development of nuclear weapons possible, but it also explained how the sun and the stars can go on radiating light and heat for billions of years.
From 1920 to 1934, scientists from many countries were applying E equals mc squared to supporting discoveries. In Britain, Francis Aston and Ernest Rutherford and Sir James Chadwick. In France, Frédéric and Irène Joliot-Curie. In Germany, Otto Hahn and Fritz Strassmann. In 1934, the first physicist who realized that the equation could be applied to military ends was the Hungarian Leo Szilard, a former student of Einstein's. He tried to persuade the American authorities to undertake research toward the development of an atomic bomb utilizing uranium fission. The Germans were at that time harvesting uranium from all over Europe, and it was clear to Einstein and other scientists why they were doing so. Einstein finally decided to sign a letter to President Roosevelt regarding the situation.
This new phenomenon could also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type might very well destroy a whole port together with some of the surrounding territory.
Almost immediately after receiving Einstein's letter, Roosevelt began setting up the necessary committees to investigate the matter further. A month after Einstein wrote his letter, Germany invaded Poland and destroyed Warsaw. The Second World War had begun. It should be stressed that from childhood, Einstein had been utterly opposed to warfare. He had, however, experienced the madness of the Nazis firsthand. Some of the greatest physicists of Germany had derided his thinking because it was not Aryan, and he had seen both his person and all of his fellow Jews threatened with extinction. Einstein's letter to Roosevelt was an act of despair. Later in the war, Einstein was opposed to the use of the bomb except as an isolated demonstration of its possible horrors. He learned of the explosions over Hiroshima and Nagasaki the way the rest of the world did, over the radio. For Einstein, it was the worst news of his life. He immediately felt responsible for this terrible event.
I committed a great error in my life when I signed the letter to President Roosevelt recommending the manufacture of the atomic bomb.
He did not participate in the actual development of the bomb, and he did participate very prominently in opposition to further uses or development of nuclear weapons.
We scientists whose tragic destiny has been to help in making the methods of annihilation more gruesome and more effective must consider it our solemn and transcendent duty to do all in our power to prevent these weapons from being used for the brutal purpose for which they are intended.
During this last decade of his life, he found himself more and more a public and political figure. Throughout his life, Einstein had been outspoken in his support of the plan for a Palestinian homeland for the Jews. In appreciation of this and his world renown, he was actually offered, though he declined, the presidency of the new state of Israel. His reason for declining was as follows.
Equations are more important to me because politics is for the present, but an equation is something for eternity.
Dr. Albert Einstein is dead at 76. A refugee from Hitler's Germany, here at Princeton he was a member for 22 years of the Institute for Advanced Study and recognized as the foremost mathematician and physicist of modern times. Since developing his theory of relativity, Dr. Einstein had been showered with academic honors, including the Nobel Prize and countless other awards the world over. This introduction is typical of the esteem in which he was held for his talents.
Albert Einstein, scientist and philosopher, Nobel laureate, loyal son of his people, friend of Israel. His daring speculations, coupled with deep researches in mathematical physics, have ranged from the microcosm of the atom to the macrocosm of interplanetary space.
A devoted apostle of peace in the atomic age his calculations helped bring about, Dr. Einstein was a friend of the world's great. Men like India's Prime Minister Nehru were among the leaders and statesmen who considered it an honor to visit him. Shy and retiring personally, his genius has revolutionized man's concept of the universe.
Albert Einstein died in the hospital at Princeton. His final words were, "I only wish I'd had more fun." The autopsy showed that Einstein's brain, which was of average size, differed in no way from those of other men. He had forbidden any memorial ceremony, which he considered repugnant. He wanted neither eulogies nor a grave. Only his closest relatives and friends took leave of him at the cremation. In accordance with his wishes, the ashes of this citizen of the world were scattered to the wind. In the years after Einstein's death, it was fashionable in the scientific world to say that Einstein's great thinking was all in the first 45 years of his life, and that he wasted his later years looking for a unity in the cosmos. In his later work, he avoided making use of quantum mechanics, even though Einstein had originally nurtured this theory. Had he further pursued his early work in quantum mechanics, as Niels Bohr and Werner Heisenberg did, the scientific community would have continued to look upon him as their most forward-looking and brilliant thinker. Part 3. Quantum Mechanics.
In 1905, the very same year that Einstein perfected our understanding of light with his special theory of relativity, he also set in motion a spectacular attack on that understanding, with the absolutely outrageous suggestion that light could carry energy only in small packages. When I shine light on this solar cell that powers this toy helicopter, the rotor starts turning. The light is kicking around electrons inside the cell, and it's the energy the electrons get from the kicks that powers the helicopter. The fact that light can kick electrons around like this was only discovered at the very end of the 19th century. Explaining it was one of the few remaining unsolved puzzles about light. In his 1905 paper, Einstein explained this photoelectric effect with a shocking generalization of an idea Max Planck had come up with in 1900 in his own desperate attempt to deal with some glaring inconsistencies in the theory of heat. Planck had noticed he could fix things up if certain kinds of energy came in lumps, which he called quanta. But nobody, including Planck himself, really knew what to do with this until Einstein realized that by boldly extending Planck's notion to make light itself lumpy, he could account for the photoelectric effect. It wasn't until 1915, 10 years after his proposal, that experiments unambiguously showed that Einstein's idea about light quanta was absolutely right. Einstein won the Nobel Prize in 1922 for using light quanta to explain the photoelectric effect, not for relativity. Although his name will always be linked with relativity, the fact is that if Einstein had never written a word about relativity, his pioneering role in quantum physics would have marked him as one of the greatest physicists in history. After launching the quantum revolution, Einstein remained an active participant. He was an inspirational and authoritative figure in the 20 years of turmoil that followed. In 1925, Niels Bohr, Werner Heisenberg, and others put together the final form of the theory, called quantum mechanics. At that point, Einstein developed serious misgivings. The first, the boldest, and the most radical of the quantum revolutionaries turned into the theory's most severe, penetrating, and conservative critic. Einstein objected most vehemently to the refusal of quantum mechanics to offer any intuitive picture of what actually happens in the world. It fails, in his own words, to represent a reality in time and space. Indeed, the theory refuses to admit that things have properties at all, unless we actually measure those properties. Ordinarily, when you want to see something, you shine light on it. In doing this, you ever so slightly disturb what you're looking at, because light exerts a very gentle pressure. But this pressure is so tiny that something as big as this rose is hardly affected at all. Suppose, though, we were looking at a much more delicate flower, like this wispy chrysanthemum. If something is delicate enough, shining light on it will disturb it, so it's impossible to learn what it was like when undisturbed. We can try to deal with this by making the light dimmer. Of course, as what we're studying gets more and more delicate, the light has to be made even dimmer. Before Einstein came up with light quanta, everybody just assumed that you could always make the light dim enough to make this disturbance completely unimportant. Einstein, however, pointed out that light is lumpy. It comes in quanta. I can illustrate the consequences with this strobe light. Ordinary light contains so many tiny quanta that you can't tell the light is lumpy at all. But when you make the light dimmer, what you're doing is reducing the number of light quanta without reducing the strength of each individual quantum. Eventually, you reach a point where the light stops appearing dimmer, and you realize that what's really happening is that the individual quanta are simply coming less and less often. So as the light gets weaker, you don't reduce the disturbance. It just happens less often. Whenever you actually manage to see the flower, it's being shaken up in the same old way. The only way you can be sure not to disturb what you're looking at is to make sure that no quanta hit it at all. And you can only do that by turning off the light completely. But with the light completely off, you can't do any observing at all. So at the atomic level, the mere act of observation unavoidably disturbs the object you're trying to study. You can then legitimately ask whether it really makes sense to say that an object has properties, such as speed, shape, or location, when the only way you can find out about these properties forces the object to change its speed, take on a new shape, or move to a different location. This is the idea behind Heisenberg's famous uncertainty principle. But for a theory to be acceptable to Einstein, it had to describe things that had properties, whether or not we insignificant humans tried to find out what they were. He asked one quantum physicist, "Do you really believe that the moon exists only when you look at it?" Though Einstein may have regarded quantum mechanics as intellectually disreputable, he would surely have agreed that in practical terms, the theory he nurtured and later attacked is successful on a scale unprecedented in the history of science. It underlies microelectronics and microbiology. It's the foundation on which modern chemistry rests. It explains how the stars burn and how the early universe evolved. And although few physicists today would go along with Einstein's philosophical objections to the quantum theory, almost all would agree that bringing general relativity and the quantum together into a harmonious whole is one of the great unfinished tasks of science.
Einstein's lifelong search was for order in the universe. His mind sought to penetrate to the very remotest reaches of space and time, to the dawn of creation, to the shape of the universe itself. He pondered the largest, most universal forces and entities: gravity, mass, energy, light, as well as the almost inconceivably insubstantial ones: the quantum, the motions of atoms and molecules, the photoelectric effect. In his mind, science, philosophy, and even religion found a fertile common ground.
How much choice did God have in constructing the universe?
Today, some 40 years after Einstein's death, other physicists following in his footsteps are beginning to catch glimpses of how the universe began. What came before the Big Bang, they ask, and from tentative marriages of Einstein's general relativity laws with the laws of quantum mechanics, there come tentative answers. There was no before, because before the Big Bang there was no time, and without a concept of time, before makes no sense. That's one of the answers. Time and space were created from something more fundamental near the beginning of the universe, is another answer. But from what? The laws only give hints, and the struggle to understand goes on. It's a struggle that may bring new insights as great as Einstein's, but without the keys that Einstein gave us, there would be no hope ever to understand. If Einstein hadn't discovered the laws of special relativity, then Poincaré or Lorentz would have done so in fairly short order. And if Einstein hadn't laid the foundations for quantum theory, then Bohr or Planck or Heisenberg would have done it within 10 years. But general relativity was different. It was uniquely Einstein's. Without Einstein, the world would have waited for many decades for somebody else to realize that gravity is caused by space-time curvature. Indeed, it was general relativity above all that made Einstein famous, and his fame was well-deserved. In the whole history of physics, just two names stand out above all others: Isaac Newton, Albert Einstein, and all the rest were lesser intellects.
Albert Einstein dreamed of things that were beyond common experience. His great theories of relativity were illustrated by examples that often dazzled or confounded most people, even many scientists. For Einstein, more than any other thinker, questioned our most basic assumptions about the nature of the world we inhabit. But as he unlocked the mysteries of the universe for himself, he found it was like a set of nesting boxes. He found more mysteries. In 1932, he made a spoken record for the League of Human Rights. He called it My Credo. The most beautiful and deepest experience a man can have is the sense of the mysterious. It is the underlying principle of religion as well as of all serious endeavor in art and science. He who never had this experience seems to me, if not dead, then at least blind. To sense that behind anything that can be experienced, there is a something that our minds cannot grasp, whose beauty and sublimity reaches us only indirectly. This is religiousness. In this sense, I am religious. To me, it suffices to wonder at these secrets, and to attempt humbly to grasp with my mind a mere image of the lofty structure of all there is.
In Demut ein mattes Abbild gleich sich zu erfassen.